Alright, chapter 12, we will be going over gases. So let's talk a little bit about property of gases. Number one, gases have indefinite volume. That means it's able to fill whatever container you put it in. And that means it also takes up the shape of the container, the volume and the shape of the container. Okay? Now, next thing, gas in comparison have low density. So for example, if you compare water, it's 1 gram per 1 mil at 25 degrees Celsius. For air, it's 1.2 grams per 1 liter. That's a huge difference right there. And the next thing is you can see a picture here. You have 1 mole of water. It only takes up 18 mils. But if you have 1 mole of gas, it takes up 22.4 liters. Gases also have high velocities and kinetic energies. That means they travel fast. So whenever you have gases, we want to talk about pressure. Every time the gas hits surface right here, it creates a force per unit area. Okay, so because the gas is gonna hit the wall, and that creates a force on that small area that it hits. So this creates pressure. Now, when we talk about pressure, number one, the more gases you have, the higher the pressure can be. If you have a higher temperature, the gases can hit the walls faster, so also be higher pressure. And then also it depends on the volume occupied by the gas. So if you have a small volume, like a smaller balloon, the gases would end up hitting the walls more often because there's less space to go around to hit the walls more often. So low pressure will be because of the big volume, and high pressure is because of a small volume. So volume and pressure are opposites. So one thing we want to know is you do have to memorize 1 atm is equal to 760 millimeters mercury, and that also equals to 760 torr. Now, these are the units here. You don't really have to memorize, but it'll be good to know. You can refer to this chart here anytime you do have to do calculations. And also, 1 Pascal is 1 Newton per meter square. But the most important thing is to memorize 1 atm equals to 760 millimeters mercury, and that equals to 760 torr. So let's go ahead and practice pressure conversions. We have 740 365 millimeters mercury. We want to convert it to atm, and we want to convert to kilopascal. So what we want to do is use a conversion factor. 1 atm is 760 millimeters mercury. And then we will do 740 millimeters mercury is what we start with. And we know we want to change it to atm, so atm goes on the top, millimeters mercury go on the bottom. 1 on the top, 760 on the bottom, cross out the millimeters mercuries, and you have 0.974 atm. So you'll have to memorize this conversion here. Now for step B, we don't have to memorize this one, but you will be given 760 millimeters mercury equals to 101.3 kilopascal. So when we have this, we start with millimeters mercury again, 740. And we know that millimeters mercury is on the bottom because we want to cancel that off. And kilopascal, the unit you want, is on the top. So 101.3 is on the top, 760 is on the bottom, cross that off, and your answer is going to be 98.63 kilopascal. So technically, if you wanted to keep 365, it will be 98.6. Let's talk about atmospheric pressure. So when we talk about gas pressure, we say anytime you have gas, it creates a pressure whenever it hits the wall of the container, right? So due to the mass of the atmospheric gases pressing downwards to Earth's surface, it also creates a pressure for the gas in our atmosphere. Now here's the composition of all the air in our atmosphere. By percentage, the highest percentage we have nitrogen gas is 78%. Oxygen gas is around 21%. Then we have argon around 1%, and then we have small amounts of carbon dioxide, neon, helium, methane, krypton, xenon, hydrogen gas, and N2O. These are all traces. One important thing to know about pressure is how we measure pressures. We use barometers to measure pressure. And the original barometer here is you just take a tube of mercury and you flip it over, invert it onto a dish of mercury. Okay, so what happens is the mercury will be pushed up by the pressure of the atmosphere because there's gas atmosphere here. I'll push it up and you'll see that at our regular atmospheric pressure here, which is 1 atm, that equals to 760 millimeters of mercury right there. You'll push it around 760 millimeters or 76 centimeters of mercury. So the height of this mercury here will tell us the pressure. At our atmospheric pressure where we are currently, we will say we are at 1 atm. Now, if you go up higher in elevation, our pressure does drop, so it will be less than 1 atm then. So what is pressure dependent on? It depends on the number of molecules of gases. So the more gases you have, the more pressure it can create. You have to make sure you keep temperature and volume constant, okay? So if we want to talk about number of molecules versus pressure, so it's pressure versus number of molecules, temperature and volume is staying constant here. If the molecules go up, pressure will also go up. So in this case here, we have a small, same size container for all three of them, okay? And actually these labels are mixed up, so let's fix that. The labels are mixed up here. So this one on the right side here is 0.5 moles of H2 because there's less, and it'll create a smaller pressure, okay? And you have more moles here, you create more pressure, and you have the most moles here of gases, you have the highest pressure right there. And this is with our temperature being constant and our volume staying constant as well. The next thing we want to look at is the effect of temperature. When we increase the temperature, our pressure is also going to go up, and you make sure you hold your moles of gas and the volume of gas as constant. So increasing temperature causes more frequent and higher energy collisions, so the pressure of the gas will go up. So let's take a look here. At 0 Celsius when it's cold, the gases move a little slower. They don't hit the walls as often, so you have a smaller ATM pressure. And if you raise the temperature, they'll run faster, they'll hit the walls more often. You'll create a higher number of pressure right there. And this is assuming we keep our volume the same, 1 liter on both sides, and we keep the same number of gases. So here's the first simple gas law. It's called Boyle's Law. Boyle's Law is going to talk about the relationship between pressure and volume. The volume of a fixed quantity of gas, so the volume, okay, fixed quantity, that means constant moles, is inversely proportional to the pressure. So volume and pressure are opposites. We kind of already knew that, but you have to make sure you keep constant moles of gas and constant temperature. Okay, so the higher the pressure, the smaller the volume will be. The lower the pressure, the bigger the volume will be. So it's opposite. So if you wrote it out, it will be PV equals to a constant because P is inversely proportional to 1 over V. V is volume, P is pressure. So then we can write P equals to the constant times 1 over V. And then we can say, simplify it, we can write P and V all on one side and leave the K on the opposite side where you have PV here. So we have PV of the first scenario equals to PV of the second scenario because the number that it multiplies to will equal to K. It will be the same number. So you can see a graph here. If you reduce the pressure, the volume actually increases right there. Alright, let's start with the first problem for Boyle's Law. We will be using P1 V1 equals to P2 V2. So this is for Boyle's Law. You have to remember P1 V1 equals to P2 V2 where P is pressure, V is volume. It says here, what volume of 3.5 liter of a gas will occupy if the pressure is changed from 730 millimeters mercury to 600 millimeters mercury. So let's take a look at what we know so far. We know that the first volume is 3.5 liter. The first pressure is 730 millimeters mercury. And they say, let's change the pressure to 600 millimeters mercury. What's the new volume? So we're missing V2 here. We have P1, V1, and P2. We are missing V2. So we gotta solve for V2. You just rearrange it, or you can fill in the numbers. And you can see that 3.5 goes here, 730 goes here, 600 will go here. So once you fill in the blanks, you can solve for what V2 is. V2 will be P1 times V1 divided by P2. So pressure 1, right here, 730, times volume 1, 3.5 liters, divided by pressure 2, 600. And you get your answer, and it's 4.3 liter. So the answer for the unit is always going to be the same unit you start off with. Let's try a second problem here. In this case here, we have a sample of neon gas, and it has a volume 250 mils at 880 torr. So this is P1, this is V1. Now, calculate the pressure P for the second scenario if the volume is increased to 1 liter. So V2 is 1 liter, assuming constant temperature. Okay, so we also obviously assume constant moles of gas, because only P and V is changing, moles and temperature will not change. So it tells us we want to convert the mils to liter. Why? Because you want to make sure your volume is the same unit. So let's keep it all uniform in the same unit. So either mils or liters, whichever, it really doesn't matter. But you just make sure you keep the same units. Okay? So we know that volume 1, we know volume 2, and we know the first pressure, we're looking for the second pressure. So we rearrange it. That means is pressure 1, 880 torr, times volume 1, divided by volume 2. And you get your answer is 220 torr. Let's do a third problem here. The third problem says you have gaseous nitrogen, so N2 gas, and it's a 65.0 liter. Okay, so let's take a look. This guy here is going to be the first volume here. So this is V1, and this is going to be P1. Okay, 745 millimeters mercury is my first pressure. 65 liter is my first volume. And this is the sample is transferred to a smaller bag, a smaller volume, 25 liters this time, at the same temperature. So remember, we assume it's the same number of sample, right? So same number of moles and at the same temperature. So only pressure and volume are changing. This is my new volume, so I'll call this V2. Okay, so now we have to solve for P2. So P1, V1 equals to P2, V2. So we will go ahead and fill the numbers in, and we'll solve for P2. So let's go ahead and put it in. 745 millimeters mercury. That's my first pressure. My first volume is 65 liter. And then the second pressure is unknown, so we'll leave that alone. And then we'll put the second volume as 25.0 liter. So then you solve for P2, which will be, if you do it on your calculator, you'll have to do 745 millimeters mercury. And then you have to multiply with 65.0 liter. And then you have to divide that by 25.0 liter. You should get your answer here for P2, and it will be in units of millimeters mercury, what we started with. And you get 1937 millimeters mercury. So that's the second pressure. Now, because we only have 3 sig figs, we can pick the answer on 1940 for our answer. All right, let's move on to the next question or next topic. Let's talk about temperature for gases. So we're going to be using Kelvin temperature scale. And if you take your gas and you cooled it down, okay, And every time you cool it down by 1 degree Celsius, the volume of the gas shrinks by 1 over 273 times. So it just keeps shrinking in volume. So just keep cooling it down, and it shrinks even more. And then if you extrapolate your data all the way down, you hit a 0 volume, which is impossible. Okay, you can't hit a 0 volume because the real gas can actually condense to turn into liquid before you can actually hit 0 volume of gas. So, but this is the 0 volume here, and you extrapolate, this is called negative 273 Celsius. Negative 273 Celsius is assigned as 0 Kelvin and is called the absolute zero. So let's recap. Absolute zero is negative 273 degrees Celsius, and that's 0 Kelvin. And remember the conversion from Kelvin to Celsius is you take Kelvin is always take the Celsius plus 273. Okay, and remember all our problems here, whenever we have temperature, we always use our Kelvin scale. We don't want to end up using Celsius because if you have a zero, it's going to make our math really weird. So you have to stick to Kelvin units. So the next law we have is called Charles' law. It's a simple gas law again. Charles' law has to do with temperature of a gas. So obviously we'll talk temperature. And it's also related to volume. So the volume of a fixed amount of gas, so fixed number of moles of gas, and at constant pressure, fixed number of pressure of right here, constant pressure, constant moles. Now the volume is going to be directly proportional to the temperature. Absolute temperature because we want to use Kelvin temperature here. Okay, so volume and temperature is directly proportional. So you write the equation V equals to KT. And if you want to put the K on one side, you will put V over T. So that means if you put an equation, you write V over T1, V2 over T2, and have them both equal to K. So this is constant right here. Now let's take a look at the picture here. If you wanted to have an original sample of gas right here, this is a free floating piston. And if we wanted to keep our pressure at 1 atm, what happens is if you heat up the gases, it's going to push the piston up to increase the volume here because of the temperature. It's kind of the same idea as like balloon with really cold air versus balloon with hot air. The balloon will just expand if we keep the pressure the same. So we're going to look at Charles' law, a problem here. We have 3 liters of gas, hydrogen gas at negative 15 Celsius is allowed to warm to 27 degrees Celsius at constant pressure. So we have the constant pressure and we have the constant amount of gas, okay? What is the new volume at 27 degrees Celsius? So we have our V1, volume 1, and our temperature 1. Now we have to convert the Celsius to Kelvin first. And then we have our new temperature, 27 degrees Celsius. That's our V2, but also convert that to Kelvin first. So we have V1, we have T1, we have T2. We're going to solve for V2. So what happens is negative 15 Celsius will turn into Kelvin plus 273 equals to 258 Kelvin. 27 plus 273 equals to 300 Kelvin. So what you want to do is solve for V2. That means it's V1 over T1 times T2 right here. Okay, so let's plug it in. V1, 3 liters. And then over T1, 258 Kelvin. And then times T2, 300 Kelvin. And you should get your answer as 3.5 liter. Okay, so we have the next question here. Our next question, it says our volume is 3 liters, 10 degrees Celsius. Remember V1 T1, but turn this into Kelvin first. What is the temperature if the gas expands to 6 liters? So this is the new volume. So we have V2 is 6 liter, V1 is 3 liter, T1 is 10 plus 273, so 283 Kelvin. And we are looking for the new temperature. So T2 right here will be equals to, so if you rearranged it, we would look like this. So if you knew that V1 over T1 equals to V2 over T2, okay, so what we would do is we want to put our T2 on the top. So we have T2 times V1 over T1 equals to V2. Okay, so that's how my T2 went on the other side. And then to get rid of just leave the T2 on the other side, we take V2. First of all, we have to divide by V1 to get rid of that term. And then we also have to multiply by T1. And that's how we get this right here. It's just showing you algebraically. If you feel like you don't really follow all this here, sometimes it's easy to just plug in all the values and then solve for it using the numbers. It still works out the same way. But you do have to understand how to rearrange your numbers. So T2 equals to T1 283 Kelvin divided by V1 3 liters times V2, which is 6 liters. And you get your answer in Kelvin, 566 Kelvin. And you can see here, when the volume goes up, the temperature goes up. Let's take a look at the third problem for Charles' law. We will be using our same formulas again. So we have a temperature 321 Kelvin. So that's my T1. And then I have a gas that's 635 mils. That's my V1. And then if the gas temperature is decreased to 216 Kelvin, that's T2. What is the new volume? So we're looking for V2, okay? So V1, T1 equals to V2 over T2. So we are going to look for the new V. So V2 equals to V1 over T1. We got to multiply that by T2. So let's go ahead and solve for it. V1 is 635. T1 is 321 Kelvin. And the new temperature is going to be 216 Kelvin. So when you put all this together here, we will get our answer as 427 mils. Alright, so let's go forward with the next simple gas law. It's called Avogadro's law, and it has to do with volume versus number of moles of gas. If you keep temperature and pressure constant, the more moles of gas, the more molecules of gas you have, the bigger the volume will be. That means volume and moles are going up proportionally the same, okay? So we have a problem here. First problem, it says, if you have an equation of the reaction and we say 12 liters of hydrogen gas is present, what volume of N2 gas is required for complete reaction? So we know the mole ratio is 3 moles of hydrogen gas to 1 mole of nitrogen gas. So because we know the moles and the volume, because temperature and pressure are held constant, we can actually just use the volume in place of the moles ratio, because they say temperature and pressure are held constant. Okay, so what we want to do is, because they're asking for new volume of nitrogen gas, we already have the volume of H2. What you want to do is say, I know the volume of H2 is 12 liters. And I know instead of 3 moles to 1 mole, we'll just say 3 liters to 1 liter, because the mole and the volume ratio will be exactly the same, because temperature and pressure are constant. So instead of using moles, you can interchangeably use liter in this case. So we have 3 liters of hydrogen gas to react with 1 liter of nitrogen gas. So you get your answer because you cross off liter of H2. Your answer will be 4 liters of nitrogen gas is required. So let's do another Avogadro's laws problem. We have gases, 2H2 plus O2 equals to 2H2O. And they say it's constant temperature and pressure, okay? So if it's constant temperature and pressure, our volume is proportional to the mole ratio. So, how many liters of O2 are required to make 45.6 liters of H2O? So we know we have 45.6 liter of H2O, okay? And we also know the mole ratio and the volume ratio of O2 and H2O, which O2 is 1 to H2O is 2. So you would say every time I have 2 liters of H2O, that's going to give me a reaction with 1 liter of O2. It's the same thing as the mole ratio, but because they told you constant temperature and pressure, we can use liters in its place. So 45.6 times 1 divided by 2, you get 22.8 liters. And this is liters of O2 because the liters of H2O is canceled off. Let's talk a little bit about molar volume. What is molar volume? Molar volume is the volume of 1 mole of gas at STP. So STP is defined as the standard temperature and pressure of 1 atm and 273 Kelvin or 0 Celsius. That means every time you have 1 mole of gas, you'll have 22.4 liters of gas. This only happens at STP. We will be using molar volume to calculate a lot of stuff, and we usually will start off by calculating molar mass. So you got to remember molar mass is going to be in units of grams per mole. Okay, so the first question says if I have 1 liter of O2 at STP and the mass is 1.429 grams, show that the molar mass of O2 is 32.0 grams per mole. So what we want to do is remember that if you have grams already, grams will be on the top, and you want to divide by the number of moles of gas. That equates to 1.429 grams. So we have 1 liter of gas is 1.429 grams. So take this liter here, we will convert this liter to moles by using the molar volume here, and we can take the moles to divide on the bottom of the 1.429. You'll get the same answer as this step here because they combine the two steps together, 1.429 and 1 liter, and then they know that 1 liter is 22.4 liters is in 1 moles. You get grams per moles right there. You get the same answer. So let me show you how you can get the alternative calculation here where we can get the moles of gas. So we have 1 liter of O2, and we know that 1 mole of O2 at STP is going to take up 22.4 liters of gas, O2. So this will give us a number of moles of gas that is 0.446. 0.0446. 0.0446 moles. Okay, this is moles of O2. Then we also know it's 1.429, so molar mass is going to be 1.429 grams divided by 0.0446 grams, 446 moles. Okay, so this will give us an answer of 32.0 grams per moles. Let's try another question here. So the next question is 3 liters of gas at STP has a mass of 5.35 grams. What is the molar mass? So remember we have 5.35 grams. We can put this on the top. We find how many liters. 3 liters here turn into moles and put the moles on the bottom. So what we want to do is take 3 liters, okay, of this gas, and then we'll know that 1 mole of the gas is going to be 22.4 liters of the gas, okay? And this will give us a mole number of 0.134 moles of gas. Okay, so we have this gas here. Now we want to find the molar mass. So the molar mass would be 5.35 grams divided by 0.134 moles of gas. This will give us an answer of 39.9 grams per mole. Okay, so the answer here would be A. All right, so let's take a look at something called combined gas laws. So we combine a few laws together. You can do any combination, but in our case here, we're doing a combination of Boyle's law and Charles' law. Okay, so we have P, T, and V are changing, but we have constant number of moles. So we end up being P times V1, P2 times V2. That's the Boyle's law part, right? And then we have V1 over T1, V2 over T2, that's the Charles law. So you can combine them together and use it for calculations. Okay? So we have a fixed quantity of gas because the number of moles is going to be constant, and the pressure and the temperature and the volume is going to be changing. So at STP, remember STP is 0 Celsius and 1 atm. Right, so we have a first problem example here. Sample gas occupies 125 mils at STP. What is the volume of the gas at 65 degrees Celsius and 320 torr? So we have the original gas here, 125 mils at 1 atm and 0 Celsius. And then we have the new, we need to look at the new volume, and it's going to be at 65 degrees and 320 torr. So P1 is going to be at STP, so 1 atm, or we use torr 760 torr. V1 is 125 mils, okay? And T1 is at STP, so it's 273 Kelvin. P2 is going to be 320 torr. V2 is what we're looking for. T2 is 65 degrees, turn it into Kelvin. So 65 plus 273, we get 338. Okay? So if you want to get V2, you'll have to take P1 V1 over T1 times T2 divided by P2, which is what you get over here. Okay, then let's fill in the blanks. We put in P1 and then P2 on the bottom, and then V1 on the top, and then we have T1 on the bottom, T2 on the top, and we also have our original P1 right here. So you just basically fill in the numbers according to the formula here, and you get your answer of 0.368 liters. You also want to make sure your units are the same, so torr and torr, Kelvin and Kelvin. Temperature must always use Kelvin. Alright, let's take a look at another question here. What is the volume of STP for a gas that occupies 1.62 liter at 616 torr at 42 degrees Celsius? So we know STP, right? STP is 760 torr, 273 Kelvin. Okay, we need the new volume. The V2 is missing, but we're given the original volume, the original pressure, and the original temperature. Always turn it to Kelvin. So if we are looking for V2, again, we'll take P1, V1, T1 right here times T2 divided by P2. So we get this. We fill in the blanks, put all the numbers in here. This is V1, this is P1, and this is T2, and then this is P2, and this is T1. Okay? And you get your answer of 1.14 in liters because the unit that's left over is liter. Torrs cancel out, Kelvin cancel out. Alright, so let's try this question now. A balloon is filled with 266 volume of helium gas. So that's the volume. and it measured at 38 Celsius and 0.995 atm. So you got to remember convert the 38 Celsius to Kelvin plus 273, okay? What will be the new volume when the temperature is lowered to negative 76 Celsius, change it to Kelvin, and the pressure is 0.561 atm. So we do the same thing again, okay? We use volume 2 equals to this formula here. So if you don't remember how we got the formula, you got to remember P1 V1 over T1 equals to P2 V2 over T2. So then if we are looking for the new volume, V2, it will be P1 V1 T1 times upside down of this, so T2 divided by P2. So we just fill in the blanks there. Okay, and then we gotta also see, make sure the 38 degrees Celsius is turned into Kelvin, and negative 76 Celsius is also turned into Kelvin. So these are the values here. So 197 is going to be our temperature 2, and 311 is going to be temperature 1. And our answer is going to be 299 in liters. Alright, so let's talk about ideal gas law. We want to combine all our simple gas laws and it becomes ideal gas law. So we had P and V to talk about before, and then we have V divided by T, right? So if you put them into a combination, ideal gas law is PV equals to nRT. So P is pressure in ATM, V is volume liter, N is number of moles, R is the gas constant, T is the temperature in Kelvin. Now the gas constant is given to us as 0.0. R is a gas constant. So let's rewrite that. R is the gas constant. And that will be 0.08206 liter ATM divided by moles Kelvin. Those are our units, okay? So that's the ideal gas law. We'll be doing some calculations based on it. So they're saying the first example question that we have, R is derived from conditions at STP. Calculate R. So what is R? So we already know R is a constant. It's given in our periodic table in the charts, but we can actually calculate it as well. Let's put it together. Pressure of STP is 1 atm. Temperature of STP is 273 Kelvin. STP volume is 22.4 liters and 1 mole of gas. Okay, so let's plug it all in. We solve for R. We have to make sure our units is correct, okay? Because if you don't have the correct units, our R will be a different number. You have to make sure you use liter, atm, moles, and Kelvin, because that's a unit of R. So in this case here, PV divided by NT gives you R. So you have PV NT. You get 0.0821 liter atm moles per Kelvin. And that's the same thing as 0.08206, just that 3 suffix is 821. Let's take a look at a problem for ideal gas law here. How many moles of helium are contained in a 0.9 liter container at 30 degrees Celsius and 0.8 atm? So we use PV equals nRT. Remember, we got to use all the correct units. So atm is good, liter is good, but temperature is no good. We need to convert it to Kelvin. So what we want to do is we have our Kelvin now is 303 Kelvin, liters and atm, and we have to solve for N, number of moles equals to PV divided by RT. Plug all those numbers in, PV, RT, and you see all the units cancel off. The liter cancel off, ATMs cancel off, Kelvin cancels off, you have moles left over. So our answer here is 0.0289 moles of helium gas. Next question here. Our next question, our volume here, what is the volume that will be occupied by 0.393 moles of N2 gas at 0.971 atm and 24 degrees Celsius? Remember, convert this to Kelvin, never use Celsius. So we want to go ahead and convert it to Kelvin, plus 273, you get 297 Kelvin. We can keep the moles and we can keep the P. We want to solve for V, so V equals to nRT over P, okay? Now nRT over P, so just plug it in, nRT over P. All our units, again, will cancel off, and what's left over is liters, so 9.87 liters will be our answer. And if you do this in your calculator, you take 0.393 times 0.08201 times 297 divided by 0.971, and you should get 9.87. So we can always rewrite the ideal gas law to help us solve for other stuff like molar masses. It's pretty convenient because number of moles is grams divided by molar mass. Okay, so if you know that, we can replace the n with grams divided by molar mass right there on the bottom. And if you ever had to get the molar mass or get the grams, we can do it using our ideal gas law equation. So here's a problem. 0.210 grams of gas has a pressure of 432 torr in a 333 milliliters container at 23 degrees Celsius. What is the molar mass of the gas? So we want to be careful with our units, okay? So we can't use torr, we got to use ATM. We have to use liters. 296 Kelvin because we want to turn 23 degrees Celsius to Kelvin. And we want to use mass and grams here because our units of molar mass will be grams per mole. So to get molar mass here, you just take grams RT divided by PV. Okay, so you have this formula here. You take the grams RT divided by P divided by V. You get a molar mass of 27 grams per mole. Alright, so let's try this question now. What is the molar mass of an unknown gas if 0.768 grams occupies a volume of 754 mils at 30 degrees and 342 torrs? So we gotta be real careful. We want to turn the torrs to ATM, okay? So I'll just write it down here. Instead of writing 342 torr, my pressure is going to be 342 torr. And I know I have to use the conversion 1 ATM is 760 torr. So it's really 342 divided by 760 ATM. Okay, so whatever the answer is, let's see what that is. 342 divided by 760. That ATM is going to be 0.45. Okay, so that's our first one. And then our volume is okay. We have to use liters though, so 0.754 liter. Okay, so you see why we have liters here, because we have to use our ideal gas law, right? Because it's PV and RT. And remember the N can be replaced with grams over molar mass. Okay, so I guess I'll write M here, or for me, I always write molar mass at MW. So PV equals to grams RT over molar mass. So molar mass, so right here, let's write it. Molar mass would be grams RT divided by PV. Okay, so we have P, we have V, our grams is given as 0.768 grams. And then R is given as a gas constant 0.0821 liters ATM per moles Kelvin. And then our temperature would be 30 Celsius plus 273 to get Kelvin. So we get an answer of 303 Kelvin. Now let's go ahead and plug it in. We have grams times R and then times temperature divided by pressure. And then volume, also divide that. So we'll end up keeping 3 fixed in our answer. And you put this in your calculator, you will get 56.3. So our answer would be D here. Okay, so there is an alternative way that we can do this. I wanted to show you an alternative way. So let's say you forget this formula. You completely forgot. Okay, so let's erase it. You still know the formula from, you still know molar mass is grams per mole, right? We always know that. So what you want to do is, if you remember grams per moles, and you have grams here, we got to divide by the moles to get molar mass. So all we got to do is find the moles of a gas at this condition right here. Okay, so then we can use PV equals nRT. So PV equals nRT would be, pressure is 342 divided by 760 again, right? So that's 0.45 atm. Our volume was 0.754 liter. N is what we're looking for. R is 0.0821. And then T will be 303 Kelvin. So what you do is you solve for N here. N will be basically PV over RT. Okay, so you put all those values together and you divide them. You take 0.45 times 0.754 divided by 0.0821 and divided by 303. You'll get number of moles as 0.0136 moles. Then you just take this number and put it on the bottom right there. Okay, that will give you molar mass. So if you take 0.7638 grams divided by 0.0136 moles, you should still get the answer D. It's actually simpler, but here that's an alternative way to calculate it. Let's now talk about kinetic molecular theory. So in general, we have a few theories based on how gases behave. So the first thing is that gases are really, really tiny particles. And the next assumption is that because they're so tiny, the distance between the particle is so big compared to the volume that they take up. So the volume occupied by gas is a lot of empty space in between them. Okay, lots of empty space, because the space that the gas itself takes up is really, really small compared to the distance between the gases. So gas particles have no attraction from one another, and they also move linearly, frequently colliding with walls of other particles. So these are our assumptions here. Okay, so there's more. So the next assumption is, when they do collide, when they do hit things, the collisions are elastic. Elastic collision means no energy is lost during collision. Average kinetic energy for a particle is the same for all gases, regardless of molar mass at the same temperature. So whatever the gas it is, it doesn't matter. If it's the same temperature, the kinetic energy is the same. Okay? So because kinetic energy is half mv squared, we can then say mass and velocity is going to be dependent on the kinetic energy or dependent on the temperature. If there's the same temperature, the kinetic energy is the same. But if the mass is bigger, the velocity will be smaller, will be slower. If the gas is light, so the mass is small, the velocity will be high. So gases which behave under these assumptions are known as ideal gases. So real gases deviate from ideal gas. Okay, so they behave like ideal gases over most of the wide range of temperature and pressure, but sometimes they deviate from the conditions. So they change a little bit from ideal gas. So what are the conditions? When you have super high pressure, because you squish the gases too close together. Because one of the assumptions was the gas has a lot of space in between them. If you squish them really high pressure, small volume, that assumption falls apart. Okay? And then at super low temperature, gases start to experience intermolecular interactions. Like they start to, so one of the assumptions was the gases don't interact with each other. Well, when you lower the temperature, the gases start interacting with each other. So that's when the ideal gases are no longer ideal, they become real gases at super high pressure and at super low temperature. But our conditions at STP, everything is assumed to be ideal. So the next thing is we want to talk about partial pressure, Dalton's law of partial pressure. So partial pressure just means that if you have gas 1, gas 2, gas 3, you can add pressure 1, pressure 2, pressure 3 from each gas, you get the total gas together. So each gas is behave independently, you can add them up together. Okay, so one practical uh, application here is when we collect gas or water, we have to remember that the total pressure that we collected is actually the gas plus the water vapor pressure. So in this case here, vapor pressure of water will be given in the question depending on what temperature it is, because the higher the temperature, the water vapor pressure will be higher. But you got to remember, the total pressure equals to the gas of the pressure of the just one gas, whatever gas you're collecting, plus the pressure of the water vapor at the temperature. All right, so the first problem here, they said that if you have a sample gas of oxygen gas collected over water at 22 degrees Celsius and 662 torr. 662 torr is the total pressure, okay? What is the pressure of oxygen gas? The vapor pressure of water is 19.8 torr at 22 degrees Celsius. So remember, oxygen's pressure is the pressure of the entire atmosphere, the total, which is 662, minus the pressure of water, which is given as 19.8. So 662 minus 19.8 will give you 642 torr as the pressure of just the oxygen here. All right, so we have the next question here. We have the next question is 250 mils of oxygen gas collected with water at 23 degrees Celsius. So you see how it's a different temperature and the water vapor pressure is different. So at 23 degrees, we have 21.2 torrs. And they want you to find out how much volume will the oxygen occupy at 23 degrees Celsius. So the pressure is 760 here. So what you want to do here is, number one, we know that our volume is 250 mils. Our pressure is going to be oxygen plus water, which was 760 for the total. They told you the 760 is the atmospheric pressure. So we also know that the water is 21.2. So then you can find out the pressure of just the oxygen, which is 760 minus 21.2. Okay? So 760 minus 21.2 gives you 739 torr. So this is now the pressure of just the oxygen gas. You also know the volume of the gas. Okay, so PV, and then we want to go ahead and calculate using the volume here. We have pressure and volume, right? And we have the new pressure, 739 torr here. So what we want to do, so previously we solved for 739. Let's go ahead and write that down. So that means the pressure was going to be 739 torr for the volume of 250 mils. Okay, so we'll call that P1 and V1. That's the pressure that we calculated for oxygen. So that's the pressure that we just got, because we had to take 760 minus the water vapor pressure. So that's 739. That's for the volume of oxygen gas at 250. They want you to find what the volume would be if your pressure was going to be at 760. So all you have to do is use P1, V1, P2, V2 and solve for it. So what we have is we solve for V2, okay, using Boyle's law, where you put P1 times V1 divided by P2. Put those values in. We have V1 and then P1 and then P2. You get 0.243 liters. So obviously because the pressure went up, the volume will go down a little bit. So that's the answer right there. Next, let's look at gas density. If we want to calculate the gas density, STP density is really easy to calculate. So what we want to do is we know that at STP, 1 mole takes up 22.4 liters. Okay, 1 mole takes up 22.4 liters. And we also know the grams of 1 mole, right? Which is the molar mass. So if you take molar mass, divide by the molar volume, you'll actually get the density of gas at STP. So remember, molar mass divided by molar volume will give you density of the gas at STP. Alright, so if we were to do calculation of density for chlorine gas at STP, you take molar mass of chlorine gas, 35.45 times 2, so 70.9 grams per moles. That's the molar mass. And then divide that by molar volume. You can get grams per liter. So it's 3.17 grams per liter for our density. So we have our original gas stoichiometry here. At first, we started off stoichiometry with taking grams, change to moles, moles to moles ratio, change back to grams. And then we can also take atoms and molecules, change to moles to moles ratio, atoms and molecules. We can also do volume of the gas to moles of gas, moles to moles ratio, and in turn into volume of the second gas. So when we want to talk about volume, STP molar volume is going to be real handy, 22.4 liters per 1 mole gas if it's at STP. If it's not at STP, we will be using the ideal gas law PV equals nRT to get the volumes or the moles that we need. So the next one we want to do is going to be gas stoichiometry. So here's the question. Calculate the number of moles of phosphorus needed to react with 4 liters of H2 gas at 273 Kelvin and 1 atm. That's right here. This is STP. So that's really nice. If it's STP, it kind of gives us a shortcut because this is molar volume 22.4 liters. Okay, so we want to know moles of phosphorus here. So what you want to do is take a look at moles of phosphorus, 2 moles of hydrogen. It's 1 to 6. Okay, so the ratio is 1 mole of phosphorus to 6 moles of hydrogen. And you also know that 4 liters of hydrogen gas, you can convert to moles of hydrogen gas using molar volume of 1 liter, and 1 mole is 22.4 liters. So that's what we know so far. We know that pressure is 1 atm, 273, so that's STP. Volume is 4 liters of hydrogen gas. We take it and turn it to moles using molar volume, and then we do the mole-to-mole ratio of 1 to 6. So what you want to do is start with 4 liters of hydrogen. 1 mole of hydrogen is 22.4 liters. Cross off the liters. You have moles of hydrogen. Cross off the moles of hydrogen on the bottom. It's 6 moles of hydrogen to 1 mole of P4. You get your answer as 0.0030 moles of P4. So let's try another question here. Calculate the volume of N2 needed to react with 9 liters of gas at 450 Kelvin and 5 atm. So if you notice here, there is a little shortcut. If they tell you the temperature and the pressure and it's not changing, remember if the pressure and temperature is not changing, the volume and moles are exactly the same. So instead of using the mole ratio, why don't we just use the volume ratio, just like the Avogadro's law? Okay, so if we say I have 9 liters of gas, okay, so 9 liters of gas here, I know that's H2, and I know that 3 liters of H2 will react with 1 liter of N2. So if we do that, we know that 9 liters is canceling off with 3 liters on the bottom here because that's 3 liters of H2 to 1 liter of N2. So my answer will be 3 liters of N2. So this would be a shortcut that you definitely want to recognize. But if you forgot, that's still okay. You can still calculate the moles using PV equals nRT because it's P, V, N, calculate the N, okay? R, T. And then once you use PV equals nRT, you get number of moles. Then you can convert it back. So it's just a really, really long calculation, right? So in this case here, it will be easy if you recognize the shortcut here. So let's practice one here. Something that we have to use, we actually have to be forced to use the ideal gas law. So we have the following reaction, and it says if an airbag should be filled with 1.09 atm at 22 Celsius, what solid of NaN3 is needed to fill a bag with a volume of 45.5 liter? So we have the volume, we have the pressure, we have the temperature. So we can use PV equals nRT to get number of moles, okay? And once you get a number of moles, that's the number of moles of N2, okay? And then what you want to do is go back and see how much NaN3 you need. So what you do is find N2 first, nitrogen gas. Okay, so our pressure is 1.09, that's given. Volume is given. 295 Kelvin is the temperature. And then what you want to do is calculate for the number of moles. This is number of moles of N2. So use PV divided by RT. So this is just ideal gas law. Okay, so once you get a moles of N2, then we have to take a look at 3 moles of N2 is to 2 moles of NaN3. Then we want to go ahead and calculate the amount of solid for NaN3 needed. So in this case here, if we know the amount of solid, we need to know the amount of solid. We start with the moles of N2, and then the mole ratio is 2 moles of NaN3 divided by 3 moles of N2 because you're trying to cross off the N2. And then we take the molar mass of NaN3 to get the grams of NaN3 that we need. That would give us the answer. Now, we want to keep going here. So the next question we have is what volume of O2 at 760 torr and 25 degrees is needed to fully react with 3.2 grams of C2H6? C2H6 is actually ethane, so let's go ahead and change that name there. Ethane. Okay, so we have C2H6 equation. 2 moles of it will react with 7 moles of oxygen. Okay, so let's go ahead and take grams of C2H6, turn it to moles of C2H6, do the mole to mole ratio to get moles of oxygen, and then use ideal gas law to solve for the volume of oxygen. So that's what we have. C2H6 is the grams. Let's go ahead and turn it to moles. The moles of oxygen, get volume of oxygen using PV equals nRT. So let's start. 3.2 grams of C2H6, 1 mole of C2H6 is 30.08 C2H6. Cross off the grams. So 3.2 divided by 30.8. And then we have our mole ratio. C2H6 goes on the bottom, O2 goes on the top. So 7 moles of O2 to 2 moles of C2H6. C2H6 gets cancelled off. Our answer is in moles of O2. So you put this together, you get 0.37 moles of O2. Now we're going to plug this in as N, right here in the moles. So we get the volume. So PV equals nRT, V equals nRT over P. N, R, T, and then P. And your answer is 9.1 liter. We have one last question here. What volume of hydrogen gas at 739 torr and 21 degrees Celsius is liberated by 42.7 grams of zinc when it reacts with HCl? We'll assume we have excess HCl here. So all 42.7 grams of zinc will react. So we take grams of zinc, use the molar mass of zinc to get moles of zinc. and we'll use it to mole to mole ratio of hydrogen gas. So it's 1 to 1. Once you get moles of hydrogen gas, you can use it in PV equals nRT to get volumes of H2. So let's go ahead and do that. 42.7 grams of zinc divided by 65.38 grams of zinc, because 1 mole of zinc is 65.38 grams. Cross off the zinc in grams. We have moles of zinc. Mole to mole ratio is 1 to 1. Moles of zinc is crossed off. We have 1 mole of H2. Our answer gives us 0.653 moles of H2. Now we'll plug this in into PV equals nRT. We gotta remember, you can't use torr in PV equals nRT. It is converted to ATM. So divided by 760, you get 0.972 ATM. And our 21 Celsius should be converted to Kelvin as well. Never use Celsius in the equations. So we have N 0.653, that's calculated from here. R is the gas constant. T is the temperature in Kelvin. P is the pressure in ATM. And you get your answer as 16.2 liters of hydrogen gas.